In previous videos, I've talked about using a moving average strategy. It's very, very common in the algorithmic trading world. But in today's video, I wanted to show you how to use a walk forward optimization on a portfolio of crypto data. Now, real quickly, if you haven't seen my previous videos, it would certainly be helpful. Otherwise, this might be a little bit more advanced. However, if you want to skip that and just keep watching, a walk forward moving average optimization means that you test a lot of parameters on out of sample data. And what we'll do is split our time series data into sections. It will then train with a certain set of parameters on the first section. It'll move to the next section, train, test, and we'll then continue to optimize as we move forward. And then once we have trained on a set of parameters that performs the best across all indexes, we'll then test it on an out of sample data set, and we'll be able to see whether or not when we train our moving average strategy and deploy it on data it hasn't seen before, we'll be able to see whether or not it performs well. And that will suggest whether it's an optimized strategy to deploy into the real market. So we'll be using vector BT to do this. We're not downloading any, or we're not importing anything that's super crazy. We've seen all these packages before. And in the previous video, we were only testing on Apple, but I thought it would be interesting to test it on a portfolio of different crypto coins. So we've got Bitcoin, Ethereum. I think this is Ripple. I think this is Binance, and this is, of course, is Doge. You can download this code in the description and use any symbols you want here. Everything else should be pretty click and play. We're going to get the last 5 years, and we just need the closing prices for this. And so this is our data frame at the beginning. The prices VBT rolling split splits our pricing data here, our 5-year data, into several different sections and indexes. And this is what it's going to, our end prices is where we're going to grab our best set of parameters for the moving average strategy, and then we're going to test on this out of pricing, out of indexes. It's very similar to machine learning. You're splitting your data into training data and testing data. This function here is going to simulate all of the different moving average portfolios given us an array of windows that we pass through it. And it's going to return a data frame of Sharpe ratios. Once we have the data frame of Sharpe ratios, we need helper functions to go into and find the best performing index and the best performing parameters on that index. This is the simulate best parameters function is the main difference between previous moving average videos that I've made and this one, because last time we could only pass through one set of pricing, and we needed something that would find the best slow and fast for each crypto coin. And it just will, it's not super crazy here. We're just making sure that the windows are compatible with each pricing data shape. So if you had if one coin didn't have the same amount of data as other coins, then this is what's going to be a problem for you. So we just make sure that what we're passing through has the right shape that we're trying to emulate here. And this is just a repeater. I've actually haven't used this a whole lot before, but it seems to help find the best and slow windows. And yeah, so this part is also really important. So this is the main difference here, but everything else is similar to the previous function that we had before. So we'll just get that function there. And then our windows is going to be an array of 10 through 40 here, and it's going to find the data. And then an in Sharpe is going to be our in pricing, in indexes, simulating all the parameters for these window arrays here. And then from this in sharp, we'll run our other functions to grab the best indexes as well as the best windows, and then zip those windows together to in a variable called in best windows pairs. So this part takes a little bit because we are simulating a bunch of different window uh, uh, variables across several different pricing assets, crypto assets. So let's just take a second here. This might take a few minutes. And then let's run through our helper functions. Great. So what does our out of pricing look like? It's just a data frame um, of our cryptos and whatnot. And this is the first section. So there are several sections that we can do that we're going to test on. So that's the first section. Here's the second section. Each section is 180 rows of each asset. Cool. So now we're simulating our in parameters, right, of our best performing slow and fast windows. And we are testing how well we're calculating the Sharpe ratio, or in other words, we're testing how well these windows perform on data it hasn't been trained for. So this is what we get. We have a set of split indexes that was trained on and the windows that performed for that index. There are 30 different indexes that we've calculated for, and there's, using our best set of windows is what we've tested for that section. Now what we're going to do is instead of going through all 30 split indexes and looking at all the different Sharpe ratios for those indexes and the moving averages for those, what we'll do instead is we'll pass through the values and we'll get the t statistic and the p-value. And what the t statistic is going to measure is basically like, you can almost think of it as the like average Sharpe ratio performance. So if it's negative, it suggests that the parameters that we've used on our out of sample data is mostly negative, or is returning mostly negative Sharpe ratios, which is bad. And then our p-value, if it's high, would mean that we reject the hypothesis, which is that our training parameters would perform well on out of sample data that is supposed to be simulating the market data that we haven't trained for. So once we grab those, we can see here that the t-statistic is very negative. So this is saying that the Sharpe ratios are indeed mostly negative for all of our sections, and therefore our Sharpe ratio using this set of parameters would not yield good results for us in the real world. And we have a p-value that is over 0.5 or 0.5. I can't exactly remember which one states whether you can reject the hypothesis or not, but we would have to reject. This is so high that we would have to reject with pretty good certain amount of certainty that this algorithm would perform poorly in a crypto portfolio scenario. And I'm trying to just double check to make sure. Interesting. What am I doing here? Is this just I think this is just duplication of what we're using here. I'm just gonna, we don't need this. If you want this data, you can download it in the description, and at the very bottom here, I have this link. This is where you can go and give a one-time donation. It's really, really helpful to me, and that way I don't have to take sponsors. I don't have to resort to selling a course to um, help. What's the word? Compensate my time and effort for doing these videos. I really do enjoy making them just because you guys find them really valuable. But if you want to go the extra mile, I would, you can go to this link and offer a donation. I really appreciate it. Otherwise, this is just going to be remaining free for people. And yeah, so thanks for watching, and I'll see you in another video. Take care. Bye.